Okay, so we are recording, and now we are in chapter 2. And so this will just be about descriptive statistics, basically. We have to start off with just a brief description of data itself, okay? Data, when you think of data, imagine a data file. And the data file will consist of rows and columns. Okay, so just it will have rows and it will have columns. And the rows will be subjects. Each person, each thing being recorded will have its own row. Okay, each person will have his or her own row. And the columns are the variables being collected, variables being measured. So these different aspects we are measuring. There we have subjects. Oh, the book calls these observational units. Let me just write that also. We have two types of data that can be gathered, and those would be numeric data and categorical data. Okay, so the variables can be numeric or categorical. Okay. Numeric tells us how much or how many. So things like examples are age, height, weight, number of children, you know, this might be for a person. If you're dealing with plants or something, it could be, I don't know what else. Okay, height of a plant. That was not a good example, but numeric tells us how much or how many, whereas categorical ones tell us what type or what kind. And so, you know, if we're talking about people, it could be, you know, hair color, eye color, or you know, male or female sex, things like that. There are subgroups of numerical. You have continuous versus discrete. So continuous things being like weight. If we had a really accurate scale, somebody could weigh 145.23 pounds and someone else could weigh 145.246 pounds or something, if depending on the accuracy of the scale. So everybody potentially weighs on this continuum. Whereas things like number of children, you only have a whole number of responses. You're either going to have 0, 1, 2, or 3. Nobody's going to have 2.2 children in terms of actual measurements themselves. The average of a bunch of data could be 2.2, and that's where we get, you know, in the US the average number of kids is 2 point something. But the actual measurements themselves are discrete units. Okay? From this data, we can create summary tables. Okay, so if we have categorical data, okay, we can, actually technically also with numeric data. Okay, so we can summarize data with frequency tables. Okay, so let's just imagine, here's a very simple table. let's say we've got, a bunch of people, Adam, Bob, Carla, Dana, Eric, I don't know, Frank. Okay. And then we ask, male or female, and so we got male, male, female, female, male, male. Okay, so this is, sex would be categorical, and then let's get a numeric response. Let's get their height. Okay, and so this 70 inches, and 69, and 64, and 67, and 66, and 73, something like that. So this is just some simple made-up data. Okay, we can create a frequency table. Okay, so for categorical variables, let's do a frequency table for sex. We would list off male, female, and we would have a count, or the frequency, over there. And so over here we would go through our table and we would say, how many males do we have? We've got 4. Adam, Bob, Eric, and Frank. And how many females? We have 2. Okay? We could add another column that makes it a relative frequency. And all we do is we take the frequency and we just divide it, and we do 4 over 6 gives us 66.7%. 2 over 6 gives us 33.3%. So this is a very simple example using our made-up data over here, and we have a frequency table, or a relative frequency table. Okay, and you can also combine them. We could also create a frequency table for the height. Okay, so this is for categorical data. But also for numeric data, we could do it for height. Now, when we look at our data, we just see that the numbers are listed off once. So one frequency table, we can take the height, and this is going to be a very terrible table, but I would just list off all of these heights, and I would go 64, 65, 66, 67, da 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 da, and I would count the frequency, and I would say, okay, well, there's one person who's, oh no, there's 0 people. 0 people who are 63, but then 64, there's 1. 0 people who are 65, no, 1 person who's 66, 1 person who's 67, okay? And so on and so forth, and the data would continue. We could also create bins, okay? So these both count as frequency tables. These are ways to summarize our data. Maybe I decide to go from 60 to 64, okay? And then from 65 to 69, and 70 to 74, okay? And I would say, well, how many people are between 60 and 64? And I would say, oh, there's 2 people between 60 and 64. And between 65 and 69, there is, let's just do this. So 65 and 69, I've got that, and that. I've got 3 people. And between 70 and 74, I have, did I count? I messed something up.
Yeah, you added an extra height.
I added an extra, where did I?
64 is just one person.
Oh, there's only one person between 60. I keep thinking there's somebody else. Okay. How do I erase this? There's only one person here. Okay, so I've got 1 person there, 3 people there, and 2 people. Good. And there we go. Okay. So these are both frequency tables for numeric data. I guess I could say this goes to 64.9 and 69.9 and 74.9 if we had decimals and things of that nature. I think conceptually this is okay, or is anybody having any struggle with this? Okay, so we have that. And so from this, let me, we can create graphic displays. Okay, so let's copy these things. We'll make a new page. Okay, so with the categorical data, we can create bar charts. Oops. And so with the bar charts, I would put the category across the bottom, and on the side I have an axis representing how many people. So I would mark this off. So I go 1, 2, 3. These numbers should be equally spaced out. They're not exactly. And so I have 4 males and 2 females. And maybe I'll fill this in. And for and so that's bar charts, okay? Stylistically, we leave a space between the categories, and with bar charts, the order of categories does not matter, okay? If I wanted to put the female column over here and the male column over here, that's equally valid, okay? It doesn't matter the order of the categories that we have. And so if you have, 10 different categories, you can put them in alphabetical order, you can put them in increasing order, based on the counts, different things like that. You have that option, okay? So that's for categorical data. On the other hand, for numeric data, we create something called a histogram. Okay, and so I'll do a histogram, at least for this partial data. And you start off kind of with these, across the bottom you put a number line. And then on the left-hand side you have the count, the frequency. So here I would put 1 and 2. And so I would put a little bar for at 64, and then at 67 we'd also have little units like that. And this would be my partial histogram, and of course the data continues on here, and I didn't actually fill out the entire table because I felt like it would be a waste of time. So that's a histogram, and this one would not be so interesting because each of these just show up once. But maybe if we make a histogram for our binned data, let's see. So I would generally you create bars for the left side unit of the bin, 70 and 75, and so the bar that starts at 60 represents everybody between 60 and 65, and I would need to create bars here, and I go 1, 2, 3. So from 60 to 64 we have 1 person. From 65 to 70 we have 3 people, and from 70 to 75 we've got 2. Okay, so this would be the histogram for that data right there. Okay, let me save that quickly. Let me just pull up, sorry, where did it go? this doesn't have what I want. Rats. Here it is. Excuse me. Let's say 60. All right. Whoops. So this is so anyway, histograms with more data might look something like this. Okay, so this is just, we only had 6 data points here. Okay, as you have more data points in your something, you might create a histogram that looks like this. Okay, and so this bar represents everybody who has a whatever CK concentration is, creatine whatever that, however you pronounce that. Okay, so they measured the numbers for 36 different people, and they created these bins from 20 to 40, and they counted this, and then so we see, okay, there's one person who has a concentration between 20 and 40. We have 4 people between 40 and 60, and we have 7 people between 60 and 80, and so on and so forth. And so with the histogram, we can see people towards the right have high values for whatever this thing that we're measuring is, and people on the left indicate people who have low values. Bars that are high indicate lots of people in this measurement. So this seems to be kind of like the normal measurement. A lot of people seem to have measurements between 60 and 120, and measurements much higher than that seem not to be as common until you get up to here, and maybe you have you have 2 people who have rather high measurements compared to everyone else. Okay, so with histograms, you do not have the option to rearrange columns. Okay, you cannot, especially with numeric data and histograms, you cannot change the order of these columns. Okay, and that's because the order of the columns is tied to the number line. So you can't say on a whim, I want the number 66 to come before the number 64. That's not allowed. The numbers go in order from least to greatest. And so on histograms, bars that show up on the right indicate individuals or measurements that have high values, and bars on the left indicate individuals or people who have lower values. So we have that. When you look at a histogram, you can label the high, if it has kind of this shape like this, the people that are up high, those indicate the mode, meaning people that values that are more common. And as you go to the right and the numbers drop off, that's known as the right tail of the distribution, and those on the left are indicated known as the left tail of the distribution. Okay? And actually, I'm going to just use the pictures that show up in our textbook to illustrate. Let me just zoom out here. The shapes of the distribution. This actually isn't that great. Okay, no, never mind. I'll just draw myself. Okay, so if you imagine different distributions, you can, we could imagine a histogram with lots of data points, and my bars are supposed to be equal width, but they're not. Okay, all right, maybe I should just use the pictures in the book. So you can imagine something, we have data that looks like this. Okay, so the shape of this distribution, maybe we summarize with just a curve that goes something like this. Okay, so again, remember that each bar, so this, you have to remember that there's a number line, and we have low values over here. So whatever this is, and high values over here. So this may be, how many years have you worked at this company? Okay, and so you have a few people that worked a few years, and a lot of people seem to work maybe a few years, not too many, and then you have some people who've been around for a long time. Okay, but not a whole lot. Okay, so people on the right indicate high values, people on the left low values. We can summarize this shape with kind of this hill that looks like this, and this shape is known as right skewed. Okay, and so I'm going to just put up the page from the book, and we have these other shapes. Okay, so we have skewed to the right, or right skewed, skewed to the left. Okay, so this means the bulk of people have generally larger values. You don't have very many people super high, but you got some people who are much lower. Okay, you have symmetric, where the middle is the most common, and as you go out to the right and out to the left, so values that are much higher are less common, but they show up with about as equal frequency as those that much lower. Okay, so height of people is generally symmetric. You have some really tall people, but they're not very common. And about equally common as those who are unusually tall are people who are unusually short. Okay, something like this might be something like income distributions. Okay, most people make about this much money, whatever this number is. Okay, and are there people who make, so whatever, most people in America make probably between $20,000 and $100,000 a year. Okay, or maybe $40,000 and $100,000 a year. Are there people who make $1 million a year? Yeah. More than that? Yeah. Okay, so $1 million a year is literally 10 times more than someone who makes $100,000 a year, and so they're way out to the right. Okay, $1 million more a year is 900,000 more than someone who makes $100,000 per year. And so if let's say the average is $100,000 a year. It's not, but let's say it was. Is there anybody who makes $900,000 less than the average? No, that would take you down to negative $800,000 a year, and you cannot pay someone negative wages, at least not legally, and something. Okay, and this is just the opposite type of situation, where you have people who are very low for some reason, and you don't have people that much higher than the average. So this might be a test score for exam, maybe a lot of people scoring 80 and 90, and you don't have anybody scoring over 100%. But then, yeah, you have a few people scoring, 70 points below average, getting 12% on the exam because they didn't study or something. So you have things like that. Okay, so you have skewed to the left, skewed to the right. Maybe I can, where's my snipping tool? I can include this diagram. Okay, so we'll copy that, throw this in here, and I'll just annotate this. Okay, so this could be example income. I don't even need to write example, so maybe income distribution, income in a capitalist society, I should say. Soviet Russia, not, well, ideally it wasn't that way, but it ended up that way anyway. And this might be exam scores, and this might be height, and this might be symmetric but not bell-shaped. I was going to have something like this. I don't know. Who knows? Okay. It doesn't matter. So we have different shapes here, okay? We also want to, what would I do? Okay. Yeah, you have bimodal and exponential. Oh, I don't know what has this shape off the top of my head in real-life data. I can't think of examples in real-life data, but we have that, okay? Yeah, so pen. You have something like this. Okay, this is bimodal, meaning mode being a peak, so you have 2 peaks. And if you have 3 peaks, you can call it trimodal or multimodal. it's usually 1, 2, or more. So bimodal, 2 peaks, this could be like testosterone levels in people. Okay. Yeah, everybody produces testosterone unless you have a medical condition. Males in general produce more, some males more than others, some males less than others, but generally even those males who produce less testosterone than other males produce more testosterone than highly, what would the word, testosterous women? Something, okay. So, and then women also produce testosterone, but generally much less than males, and some women more than others, and some women less than others, but generally women who produce lots of testosterone still produce less testosterone than males who produce less. And so you'll have a distribution that looks like this, okay? But yeah, could you have a woman that produces really high and is over here? Yes, okay? But generally it looks like this. This is actually how they make sure you're a man and a woman for the Olympics. It used to be simple, but now it's more complicated. And this is what they've resorted to, and I guess it's fair. Okay, let's talk about summary statistics. So summary statistics, we had frequency tables to kind of, and histograms and frequency tables to give us an idea of maybe some data here. And summary statistics summarize our data with just a single number. Okay, so we get single numbers, get a single number to summarize an aspect of the distribution of data. Okay, and we use these all the time, whether you realize it or not. You go to, let's say you go to Rotten Tomatoes, and I hope, I don't know what's going on. I might have spelled something wrong there, and it's redirecting me somewhere else, and I got scared. So anyway, you go to Rotten Tomatoes, you get these tomato ratings of different movies, and it says, this movie, Fast and Furious 7, whatever, is 70% fresh or whatever. What does that mean, right? Does that mean your enjoyment of the movie is 70%? No, it just, they've taken reviews from other critics and they said, well, 70% of these critics liked it, overall gave it a positive review, and that means, and you can take it for what it means in terms of whether this movie may or may not be worth your money. So that's what we have. We does it give you the whole picture? Does it tell you, the significance of the movie or what's happening? No, it just tells you it just shrinks down or summarizes everything about these other critics and what they had to say about the movie into just a single number. And that's essentially what we're doing here, okay? So we have numbers to tell us the center, okay? Measures of center, or statistics to summarize the center, okay? And we have the mean and the median. And I think most of you are familiar with these, and I don't think I need to spend a whole lot of time going over this. The mean is where you add up all the numbers and divide by how many you have. Or symbolically, we would write sum y over n. Okay, so this means you take every single value y in your data set. This, you add them up. This summation sign means add up all the values of y, and then you divide by how many you have, which is n. Okay, and the median is the number in the middle. Half are larger than the median, and half are smaller than the median. Okay. The mean has a nice visual representation. Let me find this. Oops. Okay. And it is that it is the balance point of our data. Okay, so the mean balance point of our data. Okay, so here we have 1, 2, 3, 4, 5, 6 different lambs. Okay, the weights of 6 different lambs, or how much weight gain they have. And the mean of these 6 different data points, so this is a dot plot. Basically, we have a number line, and we just put a dot at each of these things. So we have a lamb that weighs 10 pounds, and one that weighs, looks like 11, and 13, and I don't know, 19 pounds, and things like that. The mean is the balancing point. You put a little triangle here. This number line is balanced. Okay. This over here, this is the median. And if you were to use this as a balancing point, the little seesaw would be off kilter. Okay. So the median is not the balance point, but the mean is. Okay. The median is the point. Okay. You can't. Maybe it's hard to see, but the median is right here where 3 points are larger and 3 points are smaller. Okay? The median is where half are bigger and half are smaller, and that might not necessarily be the balance point of the data. Okay? But the mean is the balancing point of our data. Calculating the mean, we discussed already. You add up all the points and you divide by n. Calculating the median, you find the point in the middle. If you have an odd number of points, okay, so for the median, finding the median, okay, the median is always in the n plus 1 divided by 2th position. Okay, so here, you know, here are, there were 6 data points, right? And you put them in order, and so this is the smallest. Let's put these in order. 1, 2, 3, 4, 5, 6. Okay, so in this case we have n is equal to 6 data points. So n plus 1 divided by 2 would be 6 plus 1 over 2, so 7 over 2, 3.5. So the median is in the 3.5th position, which means it's between the 3rd and the 4th data point, and that's where the median is right here. Okay, so for 6 data points, median is in the 3.5th position, which means it is halfway between the 3rd and 4th data points. Once you put the data points in order. Okay, if you have an odd number of data points, the median will be one of the actual data points. Okay, and half of the data points are larger and half are smaller. Odd number of points. One of the points will be the median. You don't have to use this n plus 1 over 2th position. You can just say, you know, I've got 20 data points, so the median means half of the points will be larger and half will be smaller, so that means 10 are larger and 10 are smaller, and you can just put them in order and find the spot between the 10th and 11th point, okay? And that will make sure 10 are larger and 10 are smaller. So whichever way it is, I hope you guys are comfortable with finding the mean and the median. It should be okay. Because another key thing to keep in mind is that because the mean is the balance point of the data, the mean is affected by outliers. So if you have an extremely small or extremely large point, the mean is affected, but the median is not. Okay, so let me just write that in a different color. Okay. Mean is affected by outliers. Median is not. Let's save that. Okay. Can I go on to the next slide? All right. If we go beyond the median, we have something called quartiles. Okay. Let me find the data set that I want. Okay. So let's make box plots and quartiles. Okay. So the median is the point where half are larger and half are smaller. Half of the data is smaller. Which means half are larger. Okay. With quartiles, we have 4 of them. We have Q1, Q2, Q3, and Q4. Okay. The first quartile is the spot where 1/4 is smaller. Okay. Second quartile is a spot where 2/4 are smaller. And the third, etc., 3/4, and fourth is where 4/4 are smaller. Okay? So the second quartile is exactly the same as the median. So 2/4 is the same as a half. So the second quartile is the median. And the fourth quartile is also the maximum, the largest point in the data. So generally, when we talk about quartiles, we're really only talking about Q1 and Q3, because the other ones are redundant with other things that we have in the data, okay? So Q1 is the spot where 1/4 of the data is smaller. Q3 is the spot where 3/4 of the data are smaller, okay? So to find Q1, essentially you're going to find first find the median, then take that, split your list in half, and then find the median of the smaller half list. Median of the smaller half of the list. So find the median, split your list in half. Okay, and then Q3, do the same thing, but for the larger half. We'll do an example here in a moment. Once you have Q1 and Q3, we have something called the IQR. IQR is the interquartile range, and it gives us an idea of how spread out our numbers are. How spread out our numbers are. Okay. The range, on the other hand, also gives us an idea of how spread out our numbers are. Okay. Also does the same. But there's a difference. Okay. The IQR is calculated as Q3 minus Q1. Okay. It tells you the difference between the high end of the middle. So think of the middle 50% of your data. Okay, so you can think of like half of the world or half of the population is in the middle, and the IQR tells you the difference between the larger of your half and the smaller of that half. Okay, the middle 50%. Whereas the range is everybody, and you take the difference between the very biggest point and the very smallest point, and you get an idea of that. Okay, so if we were looking at incomes, okay, the person who you know, we look at annual incomes in the United States. I don't know, whatever. The person who makes the range would be the largest salary minus the smallest salary. Okay, and so a minimum wage job, so let's just say people who are employed full-time, a minimum wage job would be the smallest salary, and I don't know what minimum wage would be, maybe around $10,000 per year if you have a full-time minimum wage job, something around there. So that would be the low end, and then the largest salary that exists in the US, I have no idea. Let's say is like $10 million. I have no idea. Okay, maybe higher, maybe lower, whatever. So the range would be, you know, $9,990,000. Okay, that's the range of incomes for full-time jobs. That doesn't really give. I mean, that gives you an idea. That says something about wages, and just that there's a huge disparity between the largest and the smallest incomes. But it also is so so huge that it maybe not be so useful. The IQR tells you about the middle 50%. Okay, so if you look at, you know, somebody in the 75th percentile, Q3, they probably make around I don't know, $100,000. I think that's a reasonable guess. And then in the 25th percentile, you know, a quarter of people probably make, I don't know, $30,000 or something like that. Okay, and so your IQR would be 100,000 minus 30,000, and so that interquartile range would be $70,000, and that gives you an idea. And you'd say, you know, 50% of Americans or whatever make between, you know, are covered in this range of $70,000 or something like that. Okay. So that would be the IQR, Q3 minus Q1. Range is the maximum minus the minimum. So let's do a simple example with a box plot. All right, so let's take some data here. Okay, and so we are looking at Radish growth data in, what is this? Radish growth data in 3 days in millimeters after 3 days of total darkness. I don't know who did this experiment, but it was very exciting. So they grew some radishes in 3 days of total darkness, They measured how much these radishes grew after 3 days of total darkness in millimeters, and the numbers in order are as follows: 8, 10, 11, 15, 15, 20, 20, 22, 25, 29, 30, 33, 35, and 37. I hope I counted these right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Good. Okay, so let's make a box plot. And so first let's find the median, Q1, and Q3. Okay, so with 14 data points, the median will be the spot where 7 are bigger and 7 are smaller. So I'm going to, 14 data points. So I'm going to count 1, 2, 3, 4, 5, 6, 7. Okay, so this is going to be where our median is. 7 are bigger, 1, 2, 3, 4, 5, 6, 7, and 7 are smaller. Okay, so the spot halfway between 20 and 22, I can just take the average. I would do 20 plus 22 divided by 2, and I would get the median is equal to 21. Okay, it's very easy to see with numbers like 20 and 22, but if the numbers are like 20 and 46, maybe it's not so easy to see. You would just take the average of the two middle numbers. Okay, now that I have the median, I've got 7 numbers over here, and let's find Q1. So with Q1, it's gonna be the spot where half are bigger and half are smaller. So half of 7 is 3.5. So basically 3.5 numbers will be bigger, 3.5 will be smaller. So I count 1, 2, 3, and I end up right here. Okay, 1, 2, 3. Okay, so this is gonna be Q1. So Q1 is 15, and I do the same thing over for Q3, and I get this is Q3. So I've got 3 that are smaller than Q3, 3 that are bigger than Q3, 3 that are bigger than Q1, 3 that are smaller. Okay, so there we have it. That is our median and our quartiles. So what is our range? Our range would be 37 minus 8. I have a range of 29 millimeters. That's the difference between the radish that grew the most and the radish that grew the least. And then the interquartile range, on the other hand, is 30 minus 15, 15 millimeters. If we look at the middle 50% of radish growths, the thing that separates the highest of the middle and the lowest of the middle is only 15 millimeters. Okay. With a box plot, okay, a box plot looks like a box and it has whiskers. Okay, it looks like this, and the defining parts of the box are Q1, the median, and Q3. Those define the 3 parts of the box, and you have a whisker that goes up. This is the largest point that's not considered an outlier. And this over here is the smallest point not considered an outlier. Okay? If there are outliers, you indicate them with little circles. So how do we decide what is an outlier? Okay? We create these imaginary boundaries called fences. Okay? We have an upper fence and a lower fence, and they are defined as the upper fence is Q3 plus 1.5 times the IQR, and the lower fence is Q1 minus 1.5 times the IQR. Okay? Anything bigger than the upper fence or anything smaller than the lower fence is considered an outlier. And I should note that this is just one method for determining outliers. There's many different research papers in the world of statistics that have gone through what is an outlier and how do we decide. And this is a reasonable method, but it's one of many, and maybe not everybody feels the same. Okay, so anyway, let's find the IQ upper fence and lower fence for our data. Okay, so for our upper fence, we will do Q3, which is 30, plus 1.5 times the IQR, which was 15. Okay, so this will take me to 15 times 1.5 is why can't I do this in my brain today? All right, let's bring out the calculator. What is that? 22.5. Thank you. That's not helpful. Line item. Okay. Yes. So 15 times 1.5 is 22.5. So 30 plus 22.5 takes me to 52.5. The lower fence, on the other hand, would be 15 minus 1.5 times 15. So that would take me to negative 7.5. Okay? So are any of our data points considered outliers? No. Okay? So in our case, none of our data points are considered outliers. All right, so let's make a box plot. I'm going to draw a number line, and I'm going to start it off at, we'll do 5 and 10. Oh, that's not going to be enough. 5, 10, 15, 20, 25, 30, 35, 40. Okay. Okay. And I start by drawing a box at 15, 30 to define the edges of the box. And I draw a line at 21 to indicate the median. Okay. And I take my whisker down to the smallest point that's not an outlier, and that would be 8. So something around there, okay? And over here I go to the largest point that's not an outlier, and that would be 37, so something around here. So that would be our box plot. Okay. What if I have a hypothetical example here, okay, where the last number was not 37, but 60. Okay? In this case, and I've run out of space here, okay, my box plot would look exactly the same, except in this scenario, the largest point, 60, would be considered an outlier because it's larger than 52.5, okay? So 60 is an outlier because it is higher than the upper fence. So the largest point that is not an outlier is 35. So this box plot would end at 35. And it would look like that. And then I would have an outlier, and I've run out of space here. But we would have, going out to 60, I would have a dot indicating I have a data point at 60. Is that clear with everyone? Everyone's okay with that? Okay. So you'll have some exercises in your homework to draw box plots. Okay. Oh, and we are running out of time here. Okay. So the last bit that we want to talk about, so we have summary statistics, to describe spread or dispersion. Okay, we've already talked about two of those. We have the range, which we've defined as the maximum minus the minimum, and we have the IQR, which is Q3 minus Q1. We also have the standard deviation, which we might abbreviate as SD or simply as S, okay? And the standard deviation we can think of as the quote-unquote average, but it's not really the average, distance from the mean, okay? And really, when we say the quote-unquote average, we're talking about the average let me okay, so the standard deviation is equal to the square root of the variance and the variance can be thought of as the average squared distance from the mean. Okay, so they're both kind of this quote-unquote average distance from the mean, and so this is a weird concept, a weird idea, and we can go into the calculation of the standard deviation. But let's just say I've got a few data points, okay? Let's say I've got the numbers 1, 2, 3, 4, 5, okay? What is the mean of these data points? Okay, if we add these up, we do 1 plus 2 plus 3 plus 4 plus 5, and then we divide by 5 to get the mean, we get a mean of 3. Okay? So we're going to go through each point and we're going to ask, how far are you from the mean? Okay, or distance from the mean. Okay, so how far is 1 away from the mean of 3? Yeah, so the mean is equal to 3. Okay, so 1 is 2 units away. How far is 2 from the mean? 1 unit away. How far is 3 from the mean? 0. How far is 4 from the mean? 1. And how far is 5 from the mean? 2. Okay, I guess technically there would be negatives, but it doesn't really matter because we're going to be squaring these. Okay. And so the standard deviation is kind of like the average distance from the mean, but it's not really, okay? We're going to deal with the variance first, okay? So if we take each of these distances from the mean, we can square these distances from the mean, okay? So what would the squared distance from the mean be? So 1 is 2 units away from the mean. What is that squared? 2 squared is 4. 2 is 1 unit away from the mean. 1 squared is 1. 0 squared is 0, 1 squared is 1, and 2 squared is 4. Is that okay with everyone? Okay. And so for the variance, we would just take the average of these numbers, except we do something funny, and rather than adding them up and dividing by n, we add them up and divide by n minus 1, okay? And it's called Bessel's correction, and we don't need to get into it. But we take the, quote, average by adding up the squared distances, adding these up, these numbers up, and dividing by n minus 1, not n. And so we add these up and we do 4 plus 1 plus 0 plus 1 plus 4, and we divide by n minus 1. We have 5 data points, so we divide by 4 instead of 5. Is that okay? So I get 10 over 4. I get 2.5. Okay. So the standard deviation, again, don't get lost in all of this math and all of this stuff. It's just a way to describe the spread. How spread out are our numbers? When we talked about income, we said, you know, the difference between the person who makes a lot and a person who makes a little is quite big. Standard deviation is just another way to say we've got a lot of different incomes, okay? When we look at height data, the difference between the tallest person and the shortest person maybe is quite a bit different, okay? And if we look at most people, you know, most people fall within like a 1 foot range of each other or 1.5 foot range of each other. The difference there is not as astronomical as it is with income. You don't have people making 100 times as much as someone else. I mean, with income you have people making 100 times as much as someone else, but you don't have people who are 100 times taller than someone else. And that would be reflected in all of these numbers. The range, the IQR, the standard deviation would all tell you you don't have as much spread for height data as you do for income data. Okay, so anyway, this number that we came to, this is the variance. And so the standard deviation is you just take the square root of that. Excuse me. So the standard deviation is equal to the square root of the variance, and we do the square root of 2.5. That's our standard deviation. I have another video that I've created online that goes into a little bit more detail of calculating out the standard deviation, and it breaks down the formula for the standard deviation, which is given as this. But you can kind of see the different pieces of this thing. If you think of it as the average squared distance from the mean, and again, please watch the video I have recorded and posted as part of your homework, you can see that y minus y bar would be the distance from the mean for each data point that we have, right? Y bar is the mean, y minus y bar is how far that data point is from the mean. And if you square that, you would get the squared distance from the mean, and then you add them up and divide by n minus 1 to get the variance, and you take the square root of that. Okay, so it's all summed up in this formula here. You will see it also described in a little bit more detail in that video as part of your homework, and I hope it all makes sense. If you have any questions, you can send me an email. Don't hesitate. You've got a little bit of homework, things that talk about the empirical rule. I hope it makes sense as you do your homework. Again, if you have any questions, you can send me an email or come to office hours. Don't hesitate. And with that, we will end our lecture for tonight. And